failure theory is the science of predicting the conditions under which solid materials fail under the action of external loads. The failure of a material is usually classified into brittle failure or ductile failure. Depending on the conditions, most materials can fail in a brittle or ductile manner or both. However, for most practical situations, a material may be classified as either brittle or ductile. Though failure theory has been in development for over 200 years, its level of acceptability is yet to reach that of continuum mechanics. In mathematical terms, failure theory is expressed in the form of various failure criteria which are valid for specific materials. Failure criteria are functions in stress or strain space which separate failed states from unfailed states. A precise physical definition of a failed state is not easily quantified, and several working definitions are in use in the engineering community. Quite often, phenomenological failure criteria of the same form are used to predict brittle failure and ductile yield. Material failure. In materials science, material failure is the loss of load-carrying capacity of a material unit. This definition per se introduces the fact that material failure can be examined in different scales, from microscopic to macroscopic. In structural problems, where the structural response may be beyond the initiation of nonlinear material behavior, material failure is of profound importance for the determination of the integrity of the structure. On the other hand, due to the lack of globally accepted fracture criteria, the determination of the structure's damage due to material failure is still under intensive research. Types of material failure. Material failure can be distinguished in two broader categories depending on the scale in which the material is examined. Microscopic failure. Microscopic material failure is defined in terms of crack propagation and initiation. Such methodologies are useful for gaining insight in the cracking of specimens and simple structures under well-defined global load distributions. Microscopic failure considers the initiation and propagation of a crack. Failure criteria in this case are related to microscopic fracture. Some of the most popular failure models in this area are the micromechanical failure models, which combine the advantages of continuum mechanics and classical fracture mechanics. Such models are based on the concept that during plastic deformation, microvoids nucleate and grow until a local plastic neck or fracture of the intervoid matrix occurs, which causes the coalescence of neighboring voids. Such a model, proposed by Gerson and extended by Tvegaard and Needleman, is known as GTN. Another approach, proposed by Rouslier, is based on continuum damage mechanics and thermodynamics. Both models form a modification of the von Mises yield potential by introducing a scalar damage quantity, which represents the void volume fraction of cavities, the porosity F. Macroscopic failure. Macroscopic material failure is defined in terms of load-carrying capacity or energy storage capacity. Equivalently, Lee presents a classification of macroscopic failure criteria in four categories: stress or strain failure, energy type failure, damage failure, empirical failure. 5 general levels are considered, at which the meaning of deformation and failure is interpreted differently. The structural elements scale, the macroscopic scale where macroscopic stress and strain are defined, the mesoscale which is represented by a typical void, the microscale and the atomic scale. The material behavior at one level is considered as a collective of its behavior at a sublevel. An efficient deformation and failure model should be consistent at every level. Brittle material failure criteria. Failure of brittle materials can be determined using several approaches. Phenomenological failure criteria. Linear elastic fracture mechanics. Elastic plastic fracture mechanics. Energy-based methods. Cohesive zone methods. Phenomenological failure criteria. The failure criteria that were developed for brittle solids were the maximum stress, strain criteria, The maximum stress criterion assumes that a material fails when the maximum principal stress in a material element exceeds the uniaxial tensile strength of the material. Alternatively, the material will fail if the minimum principal stress is less than the uniaxial compressive strength of the material. If the uniaxial tensile strength of the material is and the uniaxial compressive strength is, then the safe region for the material is assumed to be. Note that the convention that tension is positive has been used in the above expression. The maximum strain criterion has a similar form except that the principal strains are compared with experimentally determined uniaxial strains at failure, i.e., the maximum principal stress and strain criteria continue to be widely used in spite of severe shortcomings. Numerous other phenomenological failure criteria can be found in the engineering literature. The degree of success of these criteria in predicting failure has been limited. For brittle materials, some popular failure criteria are criteria based on invariance of the Cauchy stress tensor, the Tresca or maximum shear stress failure criterion, the von Mises or maximum elastic distortional energy criterion, the Mohr-Coulomb failure criterion for cohesive frictional solids, the Drucker-Prager failure criterion for pressure-dependent solids, the Bressler-Pista failure criterion for concrete, the Willem-Warnke failure criterion for concrete, the Hankinson criterion, an empirical failure criterion that is used for orthotropic materials such as wood, the Hill yield criteria for anisotropic solids, the Saiwu failure criterion for anisotropic composites, the Johnson-Holmquist damage model for high-rate deformations of isotropic solids, the Hoke-Brown failure criterion for rock masses, the Camp-Clay failure theory for soils, linear elastic fracture mechanics. The approach taken in linear elastic fracture mechanics is to estimate the amount of energy needed to grow a pre-existing crack in a brittle material. The earliest fracture mechanics approach for unstable crack growth is Griffiths theory. When applied to the modi opening of a crack, Griffiths theory predicts that the critical stress, or for situations where the loading or the geometry are complex, the strain energy release rate approach has proved quite useful for such situations. The strain energy release rate for a modi crack which runs through the thickness of a plate is defined as where is the applied load, is the thickness of the plate, is the displacement at the point of application of the load due to crack growth, and is the crack length for edge cracks or is the crack length for plane cracks. The crack is expected to propagate when the strain energy release rate exceeds a critical value, called the critical strain energy release rate. The fracture toughness and the critical strain energy release rate for plane stress are related by where is the Young's modulus. If an initial crack size is known, then a critical stress can be determined using the strain energy release rate criterion. Ductile material failure criteria. Criteria used to predict the failure of ductile materials are usually called yield criteria. Commonly used failure criteria for ductile materials are the Tresca or maximum shear stress criterion, the von Mises yield criterion or distortional strain energy density criterion, the Gerson yield criterion for pressure-dependent metals, the Hosford yield criterion for metals, the Hill yield criteria. Various criteria based on the invariance of the Cauchy stress tensor. The yield surface of a ductile material usually changes as the material experiences increased deformation. Models for the evolution of the yield surface with increasing strain, temperature, and strain rate are used in conjunction with the above failure criteria for isotropic hardening, kinematic hardening, and viscoplasticity. Some such models are the Johnson-Cook model, the Steinberg-Guinin model, the Zerilli-Armstrong model, the mechanical threshold stress model, the Preston-Tonks-Wallace model. There is another important aspect to ductile materials, the prediction of the ultimate failure strength of a ductile material. Several models for predicting the ultimate strength have been used by the engineering community with varying levels of success. For metals, Such failure criteria are usually expressed in terms of a combination of porosity and strain to failure, or in terms of a damage parameter.